Steve. So this talk's really a follow-on from the previous talk yesterday from Leandro, and also following on a bit from what Ian Mackenzie was talking about on Saturday. So I'm going to sort of talking about using DFT to determine muon prototypes, and I'm particularly going to focus on molecular systems where the methods that have been developed are particularly efficient and relatively easy to apply. Although there are some complications now, which I'll come to. So I'll be talking about finding muon sites both in the case of a single molecule or a periodic crystal, and then looking at the muon coupling of these sites, which has been covered in various previous lectures, but how that relates to in particular the ALC spectroscopy, which is the main technique we're focused on here. And then looking at the quantum effect, the zero-point motion, and also the thermal motion of the muon, which affects the hyperfine parameters. And then Ian talked a bit about this on Saturday, molecular dynamics by ALC. I'll show some applications there. And then looking at electron dynamics and using the longitudinal field relaxation to study electron dynamics, for which we do actually need the coupling parameters for the muon in order to make a quantitative interpretation of the data. And then often we have, if we're interested in magnetic systems, which can be molecular as well as non-molecular. So we're looking at the effect of electronic order and how we probe into that. And then for the last part, I sort of look at extending from the simpler systems towards larger systems and the effect of disordered systems, and how we can use the calculations to help interpret these sorts of systems. And then this leads on to the workshop after tea, where there'll be some hands-on sessions with some software for doing ALC, finding muon sites, and doing dipole calculations. So, as I say, it sort of follows on from the muon airs approach that Leandro was talking about, when one has generates a set of random starting positions and does a relaxation for these structures, organising these sites, and then one can evaluate the magnetic properties. In particular, hyperfine parameters are the things we're particularly interested in. Now, for molecular systems, it's very helpful that we can use the knowledge of chemical bonding to give a head start for muonium addition sites. And this allows us to get relaxed structures, and we can use relatively fast semi-empirical methods, which are based on training sets for large quantities of molecular compounds. So, for example, the DFTB plus method that Leandro mentioned yesterday, but there's also a semi-empirical Hartree-Fock method, PM3, which works quite well for these systems. One thing to be aware of is that the training sets for these semi-empirical methods are basically structural and energetic, and they're not what we're interested in ultimately in this spin density. So one has to be careful that they may not always, what might be the best method. It's not always clear. So anyway, we can get reasonable structures, and then in order to get a good, reliable electronic spin distribution at the relaxed geometry, we really need to use DFTs. So although the semi-empirical methods are good for getting structures, for electronic structure, we have to revert to DFT. But it's only a single point calculation, so it's relatively efficient. So we heard about the different coupling methods in previous talks. So we have the isotropic Fermi concept hyperfine coupling, which is given using the symbol A, related to the unpaired spin density at the muon. And then we have the dipolar coupling, which again is an anisotropic coupling. And in the latter case, we often have a distribution of spin density over a molecule. So our dipolar sum is not just atoms, not just sites in the lattice, but it's also a distribution over the atoms that make up a molecule. So putting the isotropic and the dipolar part together is often useful, just to have a generalized hyperfine tensor, which gives you the isotropic part from the contact term and then the dipolar part. And it's useful to separate this into an axial term and a non-axial part. So then you have a simple set of parameters. You have the A, the D1, and D2, plus a couple of axes that entirely defines your hyperfine tensor. And of course, we can set the contact and the D2 non-axial part to 0, and then we just go back to our simple point axial dipole interaction with the point spin. So it's a sort of perfectly general approach. Now, the sort of practicalities of finding the Muon sites, sort of questions might ask, what size of basis set do I need in the calculations, and how long will it take? Well, to answer these sort of questions, you have to sort of look at convergence tests and seeing when you converge on the parameters that you're trying to establish. Now, for plane wave type codes like CASTEP, it's relatively straightforward. You just enter a cutoff energy, and you get fairly rapidly convergence on your final value. And then you can step back and decide where to place your calculations. When you're working with the Gaussian basis sets, it's a bit more complicated because you only have a finite set of basis sets usually within a sequence. But similar ideas apply. So you can look for convergence on the contact hyperfine part, but the part that's particularly sensitive to getting a good electronic structure are the dipolar parts, because they describe the spin distribution over the molecule. And again, you can see you get fairly good convergence with these different approaches. But it's important to bear in mind that the relative computational cost, so going from the left of the diagram to the right side of the diagram, is going from seconds through minutes to hours. So if you have a large, this is for a relatively small system, so if you have a large system, it can be prohibitively expensive to go to the right of this diagram. So you want to actually set your calculation at a sort of reasonable place on the computational cost scale. So we've tried some different methods, and just the ones that can be recommended on the basis of what we have experience with. In the case of a single molecule, you use a semi empirical method such as PM3 to PM7, which are all available in Gaussian. And then use a reasonable basis set and hybrid functionals for a single molecule case. For the periodic crystal case, then you have to use a different type of code. So the DFDB plus that Leandro mentioned yesterday is a good starting point. And then again, you have to do the DFT calculation to get reliable hyperfine tensors. So in that case, you want to use something like CASTEP or quantum espresso. So the hybrid approach is something that really speeds these calculations along. So it's basically using the semi-empirical method first for relaxing structure, followed by the single point DFT calculation, which then gives you an accurate enough distribution, spin distribution, hyperfine tensor. Using this method, you can deal with relatively complex systems. Another thing we have to be concerned about are the quantum effects and the zero-point motion. So the DFT is essentially a classical method for finding the potential minimum. But of course, the proton to some extent has an enhanced zero-point energy compared to that classical minimum. But the Muon even more so because of its light mass. So it has it's about 3 times larger zero-point energy than the proton in the same potential. So this often needs to be taken into account. And in fact, it will modify the hyperfine parameters in a sort of non-linear way. In particular, the stretch mode, which is the highest energy mode, largest zero-point energy, and it's asymmetric. So if you look at the hyperfine coupling as you go across the minimum, and you see that you get a rather non-linear effect. And so there'll be a bias on the high side of the bond, which will then give you a strong enhancement of the hyperfine coupling. The effects on the D parameters are not so big, so it's something one needs to correct for. And so for example, if you take these 3 modes in this TCNQ molecule, they have a combined quantum correction factor of about 10% RNA and 15% for the dipole. But that's not the only effect. So one is the enhancement of the hypertonic coupling, which is related to the rotation of the O-U bond around the plane of the molecule. And the other extreme would probably be butadiene, where once you start to get conformational motion, you start to lose spin density and get a collapse of the hypertonic coupling. But in between, you get sort of more modest behavior. So, for example, benzene or TCNQ. But you see there are different signs of behavior. So there are both vibrational effects within the molecule and within the lattice which contribute to this. So in general, it's actually a problem that one needs to take account of. Another quantum effect is the delocalization between sites in a system. So we have this large quantum zero-point energy, and we have these classical minima. But if the barriers between these classical sites are relatively low compared to the zero-point energy, it's meaningless to disregard distinct sites. And in fact, we basically have a quantum delocalized site which incorporates all these sites. You may then have a barrier for another set of sites, which may or may not see quantum tunneling or thermal tunneling. But your sites are basically supersets of classical sites. So an example of how this works in practice is with Ben Huddard looking at tantalum sulfide, which is a layered system, which is interesting as a 2D quantum magnet, which shows spin liquid properties. It was in fact the first triangle lattice spin system that inspired the RGB theory of Anderson. So it's had a renewed interest in studying as a spin liquid recently. So we did some ESR experiments and some Castet DFT to find what sites were stable in this system. And there turned out to be four sites. Two of them are sort of well in the interlayer region, and then one which is more associated with the sulfur layer, and then one that's getting closer to the tantalum layer. But if we look at the zero-point energies of these sites and the barriers between them, we can immediately see that how to categorize these sites. So this site number 4, the one in the tantalum case, the barrier to site 3 is actually quite small compared to the zero-point energy. So we don't expect this one to be stable, and anything that tried to form in the site 4 would actually go back to site 3. And then if you look at the barriers between sites 1, 2, and 3, again, they're all less than the zero-point energies. So therefore, we expect to have 1, 2, and 3 forming a single delocalized quantum site. But we can do the calculations and then do the averaging to get what hypertonic coupling we expect, and we can then do the site average to get around 7 megahertz for this case, which is then very useful for analysing the MUSR data. And there's no AB plane delocalization. When you look at the barriers in this direction, they're all more than 1 eV, so we don't expect. So it's all happening in this axis. Another aspect of quantum motion is quantum tunneling. So when we have these spatially close sites where the zero-point energy is only a little lower than the intersite barrier, then you get tunneling through the potential barrier. And the transmission coefficient is dependent on the mass and the energy difference between the state and the barrier in this form. And because we have the one mass to Muon, we have the larger zero-point energy, which helps. So we've got less barrier to go through, and also the tunneling rate is larger because of this mass term. So the end result is one has a longer tunneling range. So one was looking at something like 2.5 angstroms from ionium, whereas you only have 1 angstrom for hydrogen. And we've been studying this sort of behavior in things like solid benzene and methyl substituted benzenes. Okay, and so more conventional molecular dynamics is also something studied by ALC, and Ian talked a bit about this on Saturday. So we have these two types of ALC resonances: the delta zero ones, where the muon and the nucleus flip-flop together, which are characteristic for liquids. And then in the solid state, you have these delta one resonances where just the muon flips its spin, and these are usually the ones that dominate in solids. but we need these finite dipolar terms. And in fact, it's the modulation of these dipolar terms which gives us the link to the molecular dynamics. So molecular rotation, for example, average Hypine tensor, and in particular the dipolar terms, which will change your MLC line shape. So the example of benzene, we've seen this before, the rotation about the different axes produces a different narrowing and change in the line shape. So as an example of this in practice in a recent study is coraguline, which was of interest as a potential hydrogen storage medium, and Matteo Gaudi, who was working here, initiated this study. So this is a sort of cap-shaped molecule where we have a 5-membered ring in the middle and surrounded by other rings. If you look at the Muon addition sites on this molecule, you can have one in the central 5-membered ring, or you can then move out to one nearer the edge, R1. And then when you go to the very edge, you've got two possibilities. You can either be in a sort of radial position or a sort of tangential position with respect to the curvature of the molecule. And then one can calculate what the DFT expects for these particular sites. So here you've got two similarly broad resonances for R3 and R4. R2 is expected to be narrow, and R1 sort of somewhere in between. And what was actually measured experimentally is shown in the upper plot here. So at 40 Kelvin, the widths of the R3 and R4 resonances are a pretty good agreement with the prediction. But the R1 and R2 resonances, while they're in the position predicted by the DFT, they're much broader. And then if you go up to 410 Kelvin, the R1 and R2 don't change too much, but you get a significant narrowing, sharpening of the R3 and R4 resonances. So in terms of fit parameters, you can see the R3 and R4 have got similar width, and then they have a similar width which is also predicted for the DFT. And you then go up to 410 Kelvin. The DFT predicts a narrowing and a change of sign for this molecular rotation method effect that was discussed before. And indeed, the width is similar, but in the case of the R4, it's actually gets narrower by a larger factor. So one can conclude that there's actually different muonium or hydrogen dynamics in the case of R3 and R4, which is an interesting conclusion for the system. Okay, so the other aspect that I want to cover is electron dynamics. So we have, if you look at LF relaxation, it scales with spectral density function. So LF relaxation is a lot of spectral density of fluctuations, which is in turn is a Fourier transform of an autocorrelation from spin. So Tom described that in his third talk. So in this case, we expect to see a relaxation rate that scales with this spectral density function, but the coefficient of proportionality depends on the Hypine coupling. So for quantitative analysis, we need to know this Hypine coupling. So this is how it works. So for example, you have a simple exponential spectral autocorrelation function. You don't have this Lorentzian form for the frequency domain. And because when you study longitudinal field measurement, you're basically scanning the frequency by changing B. You basically measure this as a function of field. Now, that's just a simple localized fluctuation. What we're interested in here is anisotropic diffusive motion, which has a more complicated form. So you can express that in terms of a spin correlation function, which depends on the diffusion in 3 different axes. And if you look at the long time dependence of this behavior, which is actually expressed in terms of Bessel functions, you get the power law. And the power law depends on the dimensionality. So you get this power law n, where n is d over 2, the dimension over 2. And the corresponding spectral density is then n minus 1. So, for example, if you've got a one-dimensional system, you expect this to be a power law of half, and your field dependence to go as minus r, e to the minus r. Now, there's other possibility then. So that's the case for one dimension. For 2 dimensions, it's a bit more complicated, but you end up with a sort of logarithmic 1 over omega dependence. If you had a 3-dimensional diffusion, it's hard. It's got a very similar behavior to just localized fluctuations. So the cases you can actually identify very easily are d equals 1 and d equals 2. So an example of this in practice is this spin chain system. It's a very good molecular system which provides a nearly ideal 1D Heisenberg antiferromagnetic spin chain. It's made up of 2 types of molecule, a TCNQ-F4 molecule, which is the spin center, so it has a S equals half Heisenberg spin, and then these other molecules, which are silane dimolecules, which essentially act as spacers. So here one's looking down these chains, so the TCNQ molecules are separated by these inert spaces. So this is why I find such a good example of a spin chain system. And from Newton studies, one expects the spin-on dispersion in such a spin chain system to have this form. Now, the Muon is essentially an E equals naught probe as far as fluctuations are concerned. So we don't measure this whole spectrum. All we measure are the places where omega tends to 0. So that means that we expect a 0 and a Q equals 0 and a Q equals pi by A contribution. But to actually do quantitative analysis of the data, it was rather important to try and get the value for the high-fine coupling A. And luckily, one can take neutral TCNQF4 and do ALC on it, as you see on the right here. And that very conveniently gives us experimental values for this high-fine coupling parameters, both A and D1. So this is the case because the muon, if you come in with a muon, or sort of like with muoniums, you basically bring your spin into the neutral molecule. So you've got a mu plus and an electron minus. It's exactly the same as when you have a TCNQ minus molecule and bring in a mu plus, which is what we have as the main probe site in the chain. So we can directly use these high-fine values in the analysis. Study the field dependence and see the power laws, and then convert that to an absolute diffusion rate operating along the chain. It's quite sensitive to this high-fine coupling. It's actually a 4th power, so it's quite important to get good value for the coupling in this case. And you can then compare the hopping time you get at low temperature with the theoretical values for the spin-on transit time, and it's not too far off, maybe a factor 3 or so. Another example, following the same sort of idea, is coming back to that tantalum sulfide system I showed you earlier. So here one is interested in spin-on diffusion, but in this case we have a 2D layer system. The spin-half elements are contained in these interesting 13-member charge density wave objects, which are a bit like molecules with a delocalized spin-on. So I think the physics is quite similar. And one is looking at spin-on diffusion as you break valence bonds and move an unpaired spin from one place to another. So if you look at the LF-MUSR and compare it with the different dimensionality models, you see that the 2D model clearly provides the best fit compared to 1 or 3D. But as we don't have the simple situation we had with the TCNQ solve, where we have a related ALC resonance. So we really do have to rely here on the DFT calculations alone just to calibrate the measurements. And we can use the quantum average value we got earlier for A for this purpose. Okay, and so that's spin diffusion in a couple of cases. One is also interested in molecular systems in probing static electronic order. A particularly interesting system is kappa ET family, because it has all sorts of different properties. We have magnets, superconductors, and spin liquids within this family. All you have to do is change this X component. So it's based on this ET molecule, which forms layers, and then the anions sit in layers to separate these. So, for example, spin liquid case, you have a triangular lattice spin liquid. So we've actually done some measurements on this looking at the field dependence. So if we actually lose the spin liquid phase, if you go above about 4 Tesla in one of these spin liquid cases, you get a splitting of the transverse Muon signal at that point. So in order to interpret this, we need to sort of understand what the Muon site is and how it's coupling to what goes on in the lattice. And it's very useful that we have this magnetic member of this family. So there's if you use this particular anion, you then get a simple antiferromagnet. And the muosity measured by Isa et al. You get this internal field spectrum, which is 2 strong frequencies and maybe a couple of weaker ones as well. So then one can do Cascade plane wave DFT for this material and try and understand the spectrum. What one finds is that if you take mu+ sites, they will locate in the anion layer, where you have the negative charge, and these will give you some diamagnetic probe states. But you have another possibility. If you have muonium addition, it can then pair up with the spin that's already on your dimer, and then you'll have another way of getting a diamagnetic probe state where the muonium is chemically bonded to the molecule. In order to do calculations of spin of dipolar fields, one has to actually have an estimate of the spin density across the molecule. And Gaussian DFT is very good for this purpose and shows significant spin density localized in the center of the molecule and not so much on the edge. So you can use this spin distribution, knowledge of the magnetic structure in this compound, and then do some dipole field calculations. So we've got 112 spin elements because there are actually 8 molecules in the magnetic unit cell, and we have 14 spin centers on each molecule. So we've got 100 or 300 spin elements, depending on the magnetic structure. So for the zero field muosite case, one can actually try and line up the calculated dipolar fields with what's actually observed experimentally. And we find that a moment of about 0.6, 0.7 Ball magnetons gives a good match to the observed spectrum. But if one is, the addition sites in this case are not the central double bond, but the two outer double bonds, and possibly some anion layer contribution to these this low fit part. And then one way of testing this is to look at the proton NMR with the same spin distribution. So we can leave the muon out and just look at what the dipolar fields at the proton sites would be. This published spectrum here shows a nice splitting in the magnetic state. And using, again, about 0.6 UV for the moment on the molecule, you get a pretty good agreement with the measured spectrum. So around 0.6, 0.7 seems to be a good estimate for the moment in this magnetic system. Okay, so moving on to, so that was a fairly complex system, but one can move on to even more complex molecular magnetic systems. So this is a magnetic cluster nanodisk molecular magnet with 19 iron spins in a sort of disc-like shape. This has an ordering transition down at 1.2 Kelvin. So one of the questions is, it's a large spin, and that's a low ordering temperature, so it could be driven by dipolar coupling rather than the more usual super exchange interaction. But if one looks at the size of this, you can see it's rather a lot of atoms. In fact, the magnetic cell has 1,580 atoms and 78 iron spin sites. So the usual approach of discrete sites is going to be a bit challenged by this sort of size of molecule. I mean, if you had an awful lot of patience and computing resources, you probably could do something, but it wouldn't really be a pleasant experience. So I could switch to a different approach, basically looking at it from the opposite extreme. So rather than saying what specific sites are you stopping at, you can start by saying what happens if you have a random distribution of stopping sites within the cell. The cell is so large, what would that look like? So in this case here, you see this is what the distribution would like. It would be sort of peaked in terms of coupling at about 5-6 megahertz, or equivalent to a coupling field of about 50 millitesla. Well, actually, what's seen in the relaxation is a 2 Lorentzian relaxation, which indicates a fast fluctuation regime with a coupling that's actually got a bimodal distribution. And that's represented by the dashed line here. And in fact, if you think about the structure, this can be easily understood in terms of muons that are stopping near the core sites, and then muons that are stopping around the periphery, the sort of ligand sites. And they giving you this clear sort of bimodal distribution. So by switching to a sort of site distribution approach, one is still able to say certain things about what's going on in the system. So it's a different approach from the specific site approach. Okay, another type of sort of large systems are polymers. So this is an attempt to understand the spectroscopy of polyphyetine via oligomers. So one can take finite length polyphyetine oligomers and do the DFT calculations and look at the systematic change of the hyperfine coupling as you increase the number of rings in your oligomer chain. And of course you can do this and you can get a trend and then you can extrapolate. So this is plotted against 1 over n. So it forms a nice linear behavior against 1 over n. So you can extrapolate to the polymer limit and get a prediction of what the polymer would look like. Here's some actual data on polyhexyl phyetine, which is a regio random. So when you look at what the predicted polyphyetine spectrum is, you see you get a resonance position of about 0.7 Tesla. Now this is very much at one end of the broad band that you see in the polymer. But you, in a disordered polymer, you basically limit the conjugation length by the conformational disorder. So if you only had a conjugation length of 10 rings, that would bring you back up the curve here to about 8 kilogauss. And likewise, if you had about 5 rings, you'd be about 9.5 kilogauss. So, and that, if you then compare these limited conjugation length cases with what we actually see in the polymer, you start to make sense of the broad spectrum. So we can see that the peak in the spectrum is corresponding to a conjugation length of about 10 rings, and the sort of the minimum conjugation length may be around 5 rings, and then a small fraction of the sample has a very large conjugation length. So you can by doing systematic DFT studies combined with the experiments, you can start to interpret more complex systems. So this is very much an evolving area. One needs to apply more different techniques and improve the capabilities. I just sort of mentioned a few other ideas that are floating around for increasing the size of things that one can cope with. So there are some what's so-called linear scaling methods where instead of scaling with the usual n cubed scaling for the size of the system, you can actually go with n scaling. One example is this 1 TeV project. And this basically gets this improvement by doing intelligent truncation of the overlap intervals rather than just blindly going over all space, and making efficient use of sparse matrix methods. So these would seem to be a very, very promising area for applying to the Muon problems. And there's also a whole set of multi-scale type methods that people are using for these complex systems, where one uses the full quantum mechanical type approach in only a local region around the region of interest, in this case the Muon. And then simpler methods such as molecular mechanics are applied in more distant regions. So I think there's some scope for applying that sort of method. So how do we know for time? So just to summarise, the rapid progress has really been quite recent in these calculation methods. So it's an evolving story. But we already have quite efficient practical methods for simulating the LC spectrum molecular systems, and that's other areas may need a bit more work, but this is like a sort of first area that seems to be working quite well. And there are methods available for working with both single molecules and periodic crystal systems, which are both of interest. There are also methods being developed for dealing with these quantum delocalization effects, but further work's needed on that. And doing a full calculation of the quantum effects is quite costly, so one needs to sort of needs to work on efficient ways of dealing with this. So anyway, we've managed to put together all various collaborators working on this, various user tools, which are now available to assist with managing the site calculation problem, which can involve a lot of managing a lot of calculations and interpreting them. So the techniques development is, as I say, still required for some areas. But anyway, so this stuff really leads on to one of the workshops after tea. Will be workshop N, where we have a sample of methods that you can have a go on yourself. So one of them is CalcALC, which allows you to take a molecule and then calculate the radical, Muon radical states and products from the ALC spectra. So this is using Gaussian DFT on the SCARF compute cluster here, and it can also work with output from the plane wave cassette code. And it uses the Python library from James Law's quantum program for generating the ALC spectrum. Another program that will be available is Bernhardt's viewfinder programs. So this takes a crystal structure and then uses using cassette on SCARF, it uses the Muon type approach to find stable sites, and then allows you to explore these sites for magnetic ordered states using UVSI. And then finally, there's a dipole program which can take these sites you find from DFT and then look at magnetic states and explore the local fields expected for these. It can also do things like spin density wave system, which I think, well, tomorrow there's going to be a talk on manganese silicides, and I'm going to simulate the behavior there as well. So that's it. Thank you.
Thank you, Francis. Are there questions? Yeah, you showed in your tantalum calculations the 4 muon size, but you also showed some volume fraction of stopping, of number of muons stopping there. How did you get to those?
Oh, well, that's just a statistical. So the sites are just chosen randomly, and then they converge into. So it's like a base of attraction for each site.
So you just count the fraction of the number of calculations that you've done there.
Yeah, we don't have any information about how the process in finding the site, other than
that's why
so this seems like a reasonable first approximation
I agree.
to estimating the distribution. But in the end, they mostly couple up, so it doesn't matter. So, in other cases, they may stay separate. So, as a principle, it seems like a reasonable thing to do.
I think Andreas had a question.
Just a simple question. These programs you have on these clusters, they are freely accessible, or you have to be user of ISIS, or how is this dealt with?
Yeah, the ones on the cluster, you have to sign up to SCARF. You have to be a user collaborating with someone in the group, but that's usually fairly easy to arrange.
Any other questions? Yes.
For the kappa IT system, if we don't know the spin structure, then we cannot predict the internal field by using calculation. Is it correct?
So if you don't?
If you don't know the spin structure, so we have to know the spin structure first to predict predict the internal field by calculation.
Yes, I mean in this case there were many possibilities for addition sites, and you can only narrow them down by looking at the actual magnetic system, and then you can say that these. I mean, so intuitively you expect these double bonds to be where the muon sites are going to go, just chemically speaking. So the only issue was really whether it goes to the central one in addition to the outer ones, or just the outer ones. No, the central one requires you to bend the molecule a lot more, so it's probably precluded on that basis, but this, we can tell that experimentally by comparing with the magnetic phase.
Was the question about the magnetic structure?
Yeah, the magnetic structure.
So the actual long-range spin ordering, which way the spins, whether they go along different axes. I think.
Oh, well, that's, well, this is a, I mean, you're just measuring the modulus of when you're doing a zero field measurement, you just got the modulus of the local field.
Yeah.
So you can apply a different model for the spin structure, but it's already known from other measurements what the spin structure is. So we're basically using this as a calibration for the more difficult case, which is the spin liquid, where it's much harder to say what spin state you're producing when you apply the field.
Yeah, my question is we don't know the spin structure before that, so we need to propose several structures.
Yes, it's always the case you have to have models for the spin structure and compare to the experiment. The muons never give you the spin structure directly. They can discriminate between different ideas for a spin structure. That's all we can do.
Any other questions? Yeah, this one.
I have a question is related to one TED project. You mentioned about, is it only applicable for a system of GAP system or one-GAP system? Because the program, I suppose, you have to explore, you talk about the density matrix in the case of when you have a one-TED project. So is it only applicable for a GAP systems or on-GAP systems? Because you have to, you know that for a system of, or for instance, a semiconductor insulator, the density matrix is goes like exponential decay. So you can explore the matrix elements for a system, for a large system. So you know the density.
Yes, I think it's very much oriented towards insulator type systems.
Okay, so you can
polymers and biopolymers and things like that, which are quite extended, but don't have extended electronic states.
Yes.
So maybe it's still a question, but what's the meaning of the overlap integral basis for the future program? The very last slide before this workshop. Before this.
I think it was the very slide about future development.
Yeah, future.
With the one tech, one tech.
Anyway, the slide with the one tech.
So maybe, is it you mean that maybe the DFT with plane wave basis is better than the Gaussian one?
I wasn't saying that the hybrid multi-scale methods is that the thing you're.
Was it the intelligent truncation of integrals to do the overlap integral?
Yes, yes.
So what does it mean?
Well, it means in general they're decaying. So if you've got a large system, the regions of overlap where it's actually significant in your integral are not the whole of configuration space. So if you can have an intelligent method of truncating and concentrating in the area where they actually are significant, you can get a big gain in the computational efficiency. I mean, that's the basic idea. I don't know how much but it just seems to me like a good potential area for the future.
The one time, is it available or you need to have some sort of...
I think it's one of these things where you need to have some academic link with it. I think it's at a fairly early stage, but I think there are many other approaches. This is just one that I know about. But I think these end scaling things are something we ought to follow up as a community.
Well, I suspect there'll be more questions once you've had a go with some of these things. So maybe any other questions, if you have them, they'll come out in the workshop. So let's thank Francis again.